Okay, so we are talking about inverse functions. And again, this is a case where you may not appreciate the significance of inverse functions at this point, but later when we talk about natural logarithms, and exponentials, this will come back and be important, as well as the sine and the arc sine, or the inverse sine. You may have had those in a previous class. I'm sure you've had sine, cosine, tangent. And we'll talk about those in the second semester. Okay, so let's see, what are inverse functions? So on your calculator, you have inverse functions. For example, the natural log, ln, and e to the x are inverse functions. And then the trig functions and their inverse functions are inverse functions. So graphically what's going on is, what you would do is, if you had a function and you had a tabulation of x and y values, what you do is you switch the x value and the y value. And that would give you a plot of the inverse function. So let's just do that with this particular function. So what I'm going to do is I'm going to just pick some points off the graph just to make a table up. So let's create a table. All we need is two columns. Actually, we'll make 4 columns. Okay, so here it is. So the first 2 columns are going to be the x and the y value. So let's pick the ones where there are dots. So this is going to be -1, -4. And this one is going to be 0, -1. And let's actually put that in the third space, because I'm going to put one in between there. Maybe not, because it's going to be hard. I think we'll just do 4 of these points, because the other ones are not integers. Anyway, we've got 0, -1. This point here is 1, 2, 1, 2, and then the one right up here would be the next one, which would be 2, 5. Okay, so that would be f of x, the relationship for each value of x. There's one value of y. Now what we're going to do is we're just going to switch the x and the y. So I'll call this x prime and y prime. So now y becomes x prime. And x becomes y prime. So let's plot those 4 points. So you have -4, -1. Then you've got -1, 0. That's that point. You've got 2, 1. 2, 1, that's that point. 5, 2. And you'll see that the function here is, this relationship is a line like that. And I can extend this out so it covers the same amount of the graph. So there we go. So the blue curve is the inverse of the red curve. Now one other thing I'm going to draw a line for here, using what color? Let me pick another color. Let's pick green. So if I just draw a line from -5, -5, to +5, +5. And that green curve here is y equals x. You can notice that the function, which was the red curve, and its inverse are equally distant. And if it doesn't look like equally distant, it's because this is not quite square. Okay, so that's graphically what an inverse function is. So you can always just plot some of the points, just flip them. Okay, so there they are. and then if you plot the green curve, there it is. Okay. Now, how do you plot the inverse? Well, how do you do it analytically? Well, before we do that, let's even do another one just for the heck of it, just to be. So I'm going to get a piece of graph paper, and I'm going to plot something. And you can use your calculator for this, even if you don't understand what's going on here. You can still do this on a calculator just by plugging the numbers in. So what I'm going to do is I'm going to plot x and y. So here x equals, say, -2, -1, 0, 1, 2. And the y value, well, the function f of x, which is y, is equal to e to the x. So this, for each value of x, I'm going to plug in it into that formula. So you'll get, if you use your calculator, you'll get e to the -2 power, and that is 0.135, and then e to the -1 power is 0.368. E to the 0 is 1. E to the first power is just e, which turns out to be 2.71828. Okay, just put +1 in there. +1. No, it didn't like that. Okay, doesn't like the plus sign in there. Don't need the plus, just delete it. E to the first power is 2.718, and e to the second power is 7.39. Okay, so what I can do again is I'll call this prime for the inverse function. So what I do is y becomes x prime. And x becomes y prime. Okay, so let's plot the two functions. So I'm going to plot this first function. And what we'll do is we'll use a slightly larger scale here so we can see things. So I'm going to stretch out the scale in the x direction. This is -2, -1, 0, 1, 2. In the y direction, we'll go from -10 to +10. Okay. So first point, -2.135. So that's really close to the x-axis. -1.368. So that's a little bit below halfway. 0, 1, 1, 2.78. So it's 1, 2, 2.78. Erase that little mistake there. And 2 is 7.39. So that's 1, 2, 3, 4, 5, 6, 7, 7.4 approximately. Okay, so that's the curve. And we can kind of just do a rough sketch in between to kind of get an idea. Now, the inverse function, it says at 0.135, so this is 0.5, 0.25. So 0.25, 0.135 is going to be something like there. You get -2, which is that. X equals 0.368, so this is 0.25, so 0.368 is probably about there. The y value is -1. When x equals 1, x prime equals 1, y equals 0. When x equals 2.78, well actually that's way out here, so you get 1, like that. Okay, so what you do is you'd find out that the function looks something like this. And because I've skewed the axis, it doesn't look as symmetric, but this is the natural log of x, and this is e to the x. And they are inverse functions of each other. And if you were to draw a diagonal line, through here. So you go to 1, and this would be 2, 2 right there. So it's up 2 and over 2. And likewise, this one will go back this way. So it'll be about right there. So that's the curve y equals x. Again, it's not 45-degree angle because I've got the scales are skewed. But again, these functions are symmetric across there. So that's graphically what's going on. Okay, so now to do to determine analytically, so here's your original equation. F of x equals 3x minus 1. You first replace f of x with y. So this is the function, this is the coordinate. That's kind of the way you can think about it. But it's easier to deal with y's than with f of x's. Then what you do is you switch these two. So instead of y equals 3x minus 1, you have x equals 3y minus 1. And actually, well, there's two ways to do it. Well, you can make the substitution here. So I could say, x equals 3y minus 1. Or I can solve for x first and then change the variable. So it's 6, 1, 1/2, and does the other. So I'll show you this way, and I'll come back and show you get the same answer. So you solve for x. So you want to isolate the term with x, which is 3x. So you're going to move this to the other side. It becomes positive 1. Then you're going to divide both sides by 3, like that. And then what you do is you switch x and y at that point. So instead of x equals y plus 1 over 3, it's y equals x plus 1 over 3. And then you replace y with f to the minus 1 power. So this minus 1 here is not an exponent. It's telling you that you're taking the inverse function. So if you ever have f to the minus 1 power, it means the inverse function. So the inverse of the original function, the inverse of this function, is this function. Let's just do the same thing, but make the change earlier. So the other way would be to replace y with x and x with y, then solve for y. So how would you do that? Well, you'd bring this over. So you'd have x plus 1 equals 3y. Switch the sides to get the variable that you're trying to solve for on the left-hand side. And then divide by 3. So you get y is equal to x plus 1 over 3, which is the same thing we got here. So here we switch the variables after we've done, so when we finish solving for x, here we switch the variables and then solved for y. And then you say f prime of x, or not f prime, but f to the minus 1 equals x plus 1 over 3. So if we plot these two functions, so let me get the graphing program up. Okay, let's try it again. There we go. So if we plot the first function, which is the original function, 3x minus 1, and then we plot the inverse function, which was x plus 1 over 3. Quantity x plus 1 divided by 3, and I graph that, and I'm just going to change this shape a little bit. It's not quite, well, it's pretty close to the square. And then the final thing is I'm going to plot that diagonal line, y equals x. And so there you go. And that was actually the first problem we did graphically. Here it's doing it analytically. So you take the original equation, you replace f of x with y, solve for x. This is originally solve for y, solve for x, replace x with y and y with x, and then say y is equal to f to the minus 1 of x. Let's do one more. So let's say f of x equals 4x minus 7. Okay, first thing you do, replace f of x with y. Solve for x. Okay, so let's move this over to the other side. So it becomes positive. Switch sides. When you switch, you can just keep the sign, as long as you switch everything. Then divide by 4, so you'll get x is equal to y plus 7 over 4. Then you replace x with y and y with x. And then finally you say that, did it again, f to the minus 1 power is equal, f to the inverse function of the original function is just x plus 7 over 4. Okay, so what are the requirements for a function to have an inverse? Because not all functions have inverses. All inverses have to have a function to start with, but these are the requirements. The function must be one-to-one, which means for each value of y, there's only one corresponding value of x. And also, for each value of x, there's only one value of y. So to be a function, this is, for each value of y, there's only one corresponding value of x. That's not the definition of a function. The definition of a function is the opposite. It's so a function, so that's the function for each value of x, there is one corresponding y value. So we put this additional requirement, is not only is there only one value of x for each value of y, but there's only one for each value of x is only one value of y, but for each value of y there's only one. Okay. So here's some examples. So what you do is you do both a vertical and a horizontal line test. So the vertical line test, you draw a vertical line, see if this vertical line crosses the function more than one place, or the relationship more than one place. If it doesn't, then it's not just a relation anymore, it's a function. So that's the vertical line test. Then to be a function that has an inverse, you take a horizontal line, do the same thing. You go up and down. For each value of y, there's only one value of x. So this is a horizontal line test. And this passes the horizontal line test as well. So it passes the vertical line test, which makes it a function, and it passes the horizontal line test, so it has to pass both of them to be a one-to-one function. What it means is for each value of x, there's one value of y, and for each value of y, there's one value of x. Okay. So, for example, the quadratic function, as me calling it a function implies, it is a function. So I draw a vertical line. That's not very vertical. It passes the vertical line test, no matter where I take it in the domain. You're only going to intersect at one place. But if I take a horizontal line, like this, you can see that here for every value of y, this value y, there's two values of x. So we'd say this is one-to-one. This is not one-to-one. So we can have an inverse of this function. And actually for the entire domain. This one, we can't have an inverse for the entire domain. Now, what did I say? Entire domain. Why did I add that in there? Well, because if I take the function and I limit the domain to greater than 0, so let's say limit the domain for x greater than or equal to 0. Yeah, that's this part of the curve. And so you can see that this part of the curve does satisfy the horizontal line test, because this part doesn't exist anymore because I've taken it out because of me limiting the domain. So basically what you can say is sometimes you can limit the domain of the function to make it 1, 2, 1. So if I said, f of x equals x squared, and x can only be positive, 0 or positive, then this combination is 1 to 1. Without the limiting the domain, it is not 1 to 1. So there is, if I just said f of x is x squared, there is no inverse to that. But with this domain, and we'll see this for the natural log and the exponential function, you don't need to worry about that. But when it comes to the trig functions, you do have to worry about that. So that's what that says. You can have an inverse function by limiting the domain of the function. And that's where I've wiped out that one side. Okay, so what can we say about inverse functions? Let's think where we are. Inverse functions you can create by taking x and y values for the original function, just switching the x and y values, plot the resulting function. The next function, where you've switched the x and y, that's your inverse function. Analytically, we have a procedure, about 5 or 6 steps. To have an inverse function, the function has to be 1 to 1. And you can create a function that is originally not 1 to 1 by limiting the domain and making it 1 to 1. There's another, so before we talk about this one, let's make 2 more comments. One is they're symmetric around the line y equals x. So if you plot 2 functions and they're symmetric around the line y equals x, then they're inverses of each other. And secondly, what's the second thing? Can't think of the second thing right now. It has something to do with what I was just about to do. So let me go back and look at this and see if I can figure out what it was. Oh, well, yeah. So the other thing about inverse functions is that the composite function f of g of x is x, and the composite function g of f of x is x. So not only do they have those other properties, but the composite function always equals x. So, where is this going to be important? We're going to do it developing using lines, but it's more important for things like the natural log. So one example would be the natural log of e to the x equals x, or e to the natural log of x equals x. So this is a composite function, f of g of x and g of f of x. And it allows you to solve, if you have an equation like e to the 4x plus 2 equals 7, how do you solve for x? Because it's not an algebraic equation. So this will help us do that. Again, that'll be later. That'll be later in this semester. The other special case that we're going to use a lot is the sine of the inverse sine of x equals x, and the inverse sine of the sine of x equals x. And that will allow us to solve equations, trigonometric equations, for the unknown variable x. So we've, in the past, algebra 1, algebra 2, we've always solved for x. Or we solve for y, but then we may say what values of x does y equals 0, and then we solve for x. So there's just a different set of functions that we haven't dealt with before. Okay, so back to this example. So let's say f of x is 3x minus 1, and g of x is x plus 1 over 3. We don't know that they're inverse functions. The way that we could check that they are inverse functions is to do the composite function. So f of g of x, what you do is you stick g of x in for x. and then simplify it. So you'd have 3 times x, but x is x plus 1 over 3. So that's f of g of x, and then you have minus 1. And if you go the other way, g of f of x, you plug this into there. So for x, you'll put in 3x minus 1. So instead of x plus 1 over 3, we have 3x minus 1 plus 1 over 3. Okay, so if we take each one of those and we just simplify it, well, what will happen is this will cancel out with that. So f of g of x is equal to x plus 1. So these cancel out, so you just have x plus 1 minus 1. Well, plus 1 minus 1 is 0. You get x, so check. Then you have g of f of x. So what we're going to do here is you can just get rid of the parentheses. These cancel out, go to 0. So you end up with 3x over 3. 3's cancel out and become 1. You get x. So because f of g of x is x and g of f of x is x, then we know that these are inverse functions of each other. So here's another proof that these two are inverse functions of each other. So f of g of x. So what we do is we take the original function, f of something, and for x we stick in x cubed minus 3. So x becomes x cubed minus 3. We still have the plus 3. See the 3's cancel out, go to 0. So we have the cube root of x cubed, which is x. And then the other way, g of f of x, take this function, something cubed plus minus 3, and instead of x we stick in that. So we have the cube root of x plus 3 cubed. So anything, the cube root of something, the cube of something cube rooted is just whatever's inside there initially. So that becomes x plus 3. This just comes down unchanged. Move the parentheses. This plus 3 minus 3 equals 0, and you get x. So check, check. Hence, these two functions are inverses of each other. And these are what the functions look like. So if I draw a diagonal line, and it goes, let's see, 5 and 5, so that goes to right there. And then we pull it, so you see where the functions intersect, you know, where they cross. I went to the wrong place here. There we go. So where these cross this line of symmetry, they equal each other, and they flip. So you can see it's symmetric. Okay, so that's pretty much it. Here's replace x with y. So here's the kind of the review of inverse functions. You can take ordered pairs and switch the ordered pairs, make x, y, and y, x. Inverse functions are symmetric around the line y equals x. The original functions must be one-to-one functions. So we use the horizontal line test to show that they're functions, and then we use the vertical line test to show that they're functions, and then use the horizontal line test to show that they're one-on-one functions. You can also solve algebraically for the inverse function, which we did a few times. And the composite functions f of g of x and g of f of x of the two functions, the original function and its inverse, end up being equal to x.